This is Sung, and I'm the Principal and Director of Sky Academy. And in the last episode, we got to see something that was quite revealing for us, right? We analysed exponential curves. Now, this is an exponential curve that we looked at in the last episode, and we got to see that for an exponential curve, the y, the differential or the derivative of an exponential curve is proportional to the curve itself, okay? Or in other words, when you differentiate an exponential curve, you actually get another exponential curve, okay? And we got to see that as a trend, but in this episode, I'm going to prove it using first principles, using differentiation techniques that we learnt in previous chapters, okay? So I'm going to show that the case. But what I want to do in this episode is basically start off by going through the premise that we looked at in the last episode. And that was this. The derivative of an exponential function is another exponential function. And that exponential function is proportional to the original function. Okay? So let's have a look at this. If f of x is equal to a of x, so if you've got a function which is an exponential function in form, okay, then the derivative of that exponential function is actually the original function times a constant. So in other words, the exponential function is equal to the derivative, or is proportional to the derivative, all right, which means it's equal times the constant, okay? Good. All right, so I'm going to show you why and how this works using first principles, okay? So if you've got, and I'll do it on the board, if you've got f of x, which is equal to a of x, we're going to look at the derivative of a of x, right? So basically, the derivative by first principles looks like this. The limit of h approaches 0, right? It's starting to look familiar. The limit of h approaches 0 is equal to f of x plus h minus f of x all over h. Do you remember that? Good. So what we're going to be doing is substituting x plus h into that, which gives you a to the power of x plus h minus a to the power of x all over h. Do you see that? Alright, so what I want to do now is basically use some algebraic manipulation to show you what's going on. A to the power, that's going to be equal to a to the power of x times a to the power of h. Do you see that? X plus h can be broken down to a to the power of x times a to the power of h using the index laws minus a to the power of x over h. I want to factorise the a to the power of x out, and we get that. Do you follow? Right. Alright. So the next line is we're gonna take that a to the power of x right up the front. Yes? Alright? So we're left with the limit of h approaches 0 for a to the power of h minus 1 over h. Right? What I want to basically say, right, is that this will be some constant. It'll be a constant term. Because what I want you to see is that a is a constant term, right, determined by the base of the exponential function. H and h are going to approach 0, alright, and then you've got the minus 1, okay, so you've got no variables here, right, except this h approaching 0, alright, and what I want you to see though, and I guess the next question that you'll ask is, how do you know that the limit is going to be a constant term as opposed to shooting off into infinity somewhere, okay? Well, what I want you to do is choose a constant, for example, the constant, choose a constant for a. So for example, let a equal to 10, all right? So I'll basically use this over here. So let's try for example, if a was 10, and we'll try and consider f of x equals 10 to the power of x. So the f dash of x is going to be 10 to the power of x times the limit of h approaches 0 for 10 to the power of h minus 1 over h, right? So what I want you to do is basically test it out, all right? It will approach some constant, and the reason why we know that is just say make h a really small number. So let's make h equal 0.00001. Okay, so you got 5 zeros in between, right? Put that into your calculator using 0.00005, 5 zeros before it. Okay. Into that calculator, and what you will find is your answer approaches some constant. It'll be 2 point something, right? And the constant that this number will approach will always depend on the value of a. Will depend on what the value of a is. But what I want you to note is that it will be some constant. So in other words, that leads us to the conclusion that f dash of x will be equal to k of f of x, right? Which is the premise that we had over here. Got that? So this kind of shows, by first principles, that the derivative of an exponential function will be the original function times some constant. So in other words, the derivative of an exponential function will be proportional to that function, all right? Now, there's an all-important next step that I want to go through. Yes? Can you imagine what that next step will be? Can you imagine a function where the derivative of the function is not just going to be proportional to the function, but where the derivative of a function is going to equal the function of itself? So in other words, where the derivative will be equal to the original function. All right? Can you imagine that to be the case? Yes, well, there's got to be some function out there where the derivative of it is equal to itself, right? And it's going to be in the exponential realm. So in other words, it's going to be an exponential function, right? And what it will be f is equal to a of x for some special a, right? We want a value for a that the derivative of that will be equal to the original function, where k, what value would k have to be equal to? K would have to be equal to 1, all right? Because we're looking at where the derivative of the function is equal to 1 times the function itself. Yes? All right. Now, this is what I want you to know, all right? There is a special value for a, and that special value for a, it's the number e, right? E is that special number, right? And it's on your calculator. Basically, on your calculator, you should see a button that has e to the x, or it might be written as e to the box, right? And e is a very special number. It's like the number pi. Remember how pi is what we call a transcendental number? It's like 3.1428 ... It just keeps going forever. E is another number that keeps on going forever, okay? So let me just go through what E would be. Basically, what I want you to do is put e to the power of 1. And e is the number, let me just get a blue pen. E is the number, and I put it in the calculator, 2.71828 ... Okay, so E is a very special number. E is the special number where y equals to E of x gives what, I'll change it to f of x. F of x. So E is the special number where f of x equals to E of x gives f of x equaling f dash of x equaling f of x. Okay, so E is the number, E is the number 2.71828, alright, etc. It's a transcendent, it's what we call a transcendental number, like pi, alright. So it's a transcendental number like pi, and E is the special number where f of x equals to E of x gives the derivative equaling the function itself. Okay, so E is a very special number, and basically all derivatives of exponentials and logarithmic functions or exponential functions need to be brought down to the base of E, right, in order to be able to differentiate them. Okay, so I want to introduce you to this very special number. It's E, and the reason why it's so special is because that's the number where the derivative equals the function itself. Okay, thank you very much for watching.